Yeah, sure. Right.
Okay, so welcome to next talk in the session, right, which is by Stein, and it will be on regularity inheritance for pseudorandom graphs.
Yeah, thank you very much. Thank you to the organizer for inviting me and to the organizer of the semester, of the program. As someone else said before today, I'm not really identifying as a pseudorandomness, or however you say it, but my co-authors are, and they dragged me into it. So this is joint work with people from the LSE, Peter and Julia Böttcher, and Joseph Skokon. Two of them are here. So, yes. So I'm going to start with talking about regularity. It just goes. I have more slides. Promise. Maybe I was holding it the wrong way around. No, it's a backwards button. Yeah, okay, I'll just try to do this. So I was also hoping that Julia would introduce regularity, so now I have to do it. So I'm going to start with this. I'm sure you've seen it somewhere before, Regularity Lemma of Simaredi, which he used to prove the Simaredi theorem of arithmetic progression, so on. So the picture is something like this, or like the statement is this. Every graph has a partition into parts of almost equal size, so that would be plus minus 1. And you have a lot of control on the edges between the parts. So, and the control is, it's epsilon regular. I'll tell you in a second what that exactly means. And I should also tell you, you have the control only in almost all the pairs, and you also have bound on the number of partition of classes that you will have, and this is bounded. It doesn't depend on the graph, it only depends on the epsilon. So you will get a bounded for any epsilon. It will work for any graph that you have, if it's a set size. So what does this mean? And also you know about the edges that are inside these classes, that are very few, and those that are not in regular pairs are also very few. So you know these are something of order epsilon n squared, which is really a small portion. So what does it exactly mean, this regularity? So a pair is regular if for subpairs of sufficiently large size, so an epsilon portion at least on either side. The density doesn't differ much from the density of the original pair. So the density is the number of edges that you have divided by the number of possible edges, right? So I could write this also like the density between this pair and the density of the original pair. So that's what you have, and that is the regularity lemma. And then you have some properties. So one very important property that always comes up is the slicing lemma. The slicing lemma says that subpairs of regular pairs inherit regularity. So that means if I have an epsilon regular pair and some subpair which is sort of large enough, then this pair again is regular with some epsilon prime. That depends on the epsilon and how large maybe this other pair is. So the picture is something like this. This is my original pair, and then I have a subpair of sufficient size, and then I will have almost the same density also. So you can say make it a bit more precise, but if you haven't seen this, then it doesn't matter. You don't have to. You can believe me what I said. So that is something that you can call like regularity inheritance. Now you have another property that's important. It's a degree property, which says that almost every vertex has like the degree that you would expect if it was a random pair. Or you could say it has the average degree. Almost every vertex on one side will have the expected degree into the other side. And that also works for the subpairs because you have this inheritance for subpairs. So yeah, probably you might have seen this before. So yeah. I also said there's a counting lemma, or I don't know if I said it, but this regularity method, often what you use is you have you use a regularity lemma and the counting lemma together. So the counting lemma, what does it say? Say you have a graph H, and you have a big graph G, which has, for each vertex of H, it has a large class of vertices, and everywhere where there was an edge in H, you have an epsilon regular pair, actually, the edges of an epsilon regular pair. And then you know that you can count the number of copies of H in this bigger graph G, or the number of labeled copies that you have, or canonical copies. So I want each vertex, to go to the class where he's supposed to go, according to my plan that I had. So, and the number that you'll get is this one, up to some error, but which you can make small as you like, and then you have to pay for it with a regularity. So, and you want to count all the copies that come up this way. So this number that you get, if you just want to prove this for a triangle, just to let me convince you of this number, that this is the correct number, then you have the situation that's the graph you want to find, or you want to estimate the number of times it occurs here, and there is your bigger graph G, and then you just take a vertex here, and you have how many choices, like as many vertices as there are in this set, and then the neighborhoods in the other two sets, they look like this, and then you know if they're large enough, they will inherit this regularity, and so you will find several edges here to complete a triangle. So that means, what did you do? This guy had a more or less expected degree if he wasn't exceptional, but those are only few. So this degree should be about the density between this pair times the size of the other set, right? So in total you took, like you also looked here at the density, and here you had to see how many edges were there. That must be also like the density times the size of the set. So you'd come to this number. Now if you want to prove this for a bigger graph, so let's do it with this picture. How are you going to do it? So you could do it like this. You put the first vertex, and then you see, like according to where this guy that you put has neighbors, you just reduce this cluster to a smaller set, which are just the neighbors, which I will do here, but not in this one, because here is just, I don't have to put a neighbor of this other guy. So then you choose a vertex inside there, then you look at his neighbors in the other set, and you choose a vertex in the next one, then you have to restrict to the neighbors, and then you choose a vertex here, and then you finally have to here, and here you have to go from the neighborhood of the first guy, and then you have to go into the neighborhood of the second guy also inside this set, and then you have to go to the last guy into the neighborhood of this set. So, and then you choose the last vertex. So this will, every time I choose someone, it really depended on how many earlier neighbors have been embedded already, and that made this set shrink so much. So, and that gives you basically this formula up there. So that's the way you could prove this counting lemma, right? So now these things work well together, because the regularity lemma will give you this epsilon regular partition, and then the counting lemma just starts from this partition and can count the copies of graphs that you will find in the graph. So you can just apply this. If you give him some graph G, you can just apply the regularity to him, and then look in this regularized graph of the copies of the small graph you want to find. So how can you apply this? So for instance, you can prove something like this removal lemma, which says that every graph either has a lot of triangles, or we can delete a small number of edges and make the graph triangle-free. And now that a lot and few, these are this epsilon and delta, and of course they depend on each other, but that basically you can prove by taking the graph. You can delete all the edges that don't take part in the regular pairs, and then if there are no triangles, if there are no triples of regular pairs, then there are no triangles in the graph, and if there are, then there are many, and so that's all. And you can do something like property testing with this. So if you just sample some vertices, and if they induce a triangle, then you can say the graph is far from being triangle free, and if they don't, then you say it's the graph is triangle free, and you give the right output. Something like this it can be interesting. But you can also use it in other ways, like Julia had this Blowup Lemma, also came up in her talk. So there, in the same situation as before with the counting lemma, you can look at this graph G, and now instead of counting how many copies of a very small graph you have, you can just embed one graph that has almost the same size as the graph G, but it must have bounded degree, and it must sort of fit into these partition classes, have the edges in the right places. So it must look like something like that has the same structure as this graph. So. So now what happens in sparse graphs? In sparse graphs, so that means graphs with n vertices and very few edges, of n squared. So what is the problem? The problem is that regularity now doesn't mean anything anymore, because if the density of a pair is really smaller than the epsilon of the regularity, then you don't know anything about the pair. Like saying this is regular doesn't really tell you anything about how the edges are distributed. And if you have a graph of a density much smaller than this epsilon overall, then basically any partition is regular. So it doesn't really say anything. So this problem has been fixed with the sparse graph regularity, so which goes back to end of the 90s, Koherkawa and Röde. And they say, yeah, you're not measuring right. You must substitute the density with something that you can call the p density, which is you take the density as before, but you scale now by p, and p is just an appropriate small number. So instead of the density, now you consider the density divided by p, and that's what's called the p density. And then there is a sparse regularity lemma by these people, and then they had another condition, this upper uniformity condition, which was not necessary in the end. So, and they say every graph has a vertex partition into almost equal size sets, such that almost all pair are epsilon regular, but now with this property, so taking this into account, and the rest is just the same, like the number of parts is just the same, so this partition would just the same, the analog for the sparse thing. So now what does this mean? This regulator now you just, instead of measuring the density, how the density differs in the subpair and in the original pair, you just take the difference of the p density, and that's then epsilon p regular, and if the density of the pair is p, then you say epsilon regular with 0. So this is what you can do in sparse graphs. And does this mean that you also have a counting lemma for sparse graphs? And if, then what would it look like? Because it's also not so clear. This version that I had maybe is too coarse also for measuring in the sparse graph, because the error factors may be too large or somehow not right. So how was it again, this counting lemma? We had this formula here. So what would you have to modify for making a sparse counting lemma? So you would have a different regularity. You now would have this new regularity, sparse regularity notion here. You would take the p densities here instead of the original densities. And then you would have to multiply here with p to the number of edges. Because in this way, you will have the error term measured in a finer way. Like it would really depend on the densities that you have. So that would be the version that you would want. And now the problem is that if you want to prove it in the same way, this will not really work, because if you remember this picture or something like this, if you have a vertex and you look at its neighborhoods, then the neighborhoods are just too small, so they will not really inherit the regularity. So that is the problem. Before in this first picture of proving the counting lemma, we had this, and we said, yeah, there must be the edges because this is a subset that's large enough, and so there are edges between the two, and it's regular. And now it isn't, because it's just too small. So then lemma is not true, and you can also like do a concrete counterexample if you want. So this is doesn't work. But still there is some hope. So it's not so common that you don't inherit regularity in a subpair. So it's with a high probability you do inherit it if you take a random subpair. So yeah, the picture's not very maybe. And so in random graphs, for instance, you can have counting lemmas. So if you're in a subgraph or a random graph, so that was this KLR conjecture, then you do have counting lemmas, and you can have this similar counting lemma as the one I had on the slides before. And if you have another underlying structure, namely a pseudo-random graph, then you can also have it. So there was work by Kohergava, Rödel, Schacht, and Skogan for triangles. And then Condon, Fox, and Zhao have a paper where they show the counting lemmas for general graphs H. And so in our work, we have counting lemmas that are sometimes better. It depends on the graph H. So this goes via inheritance lemmas. So the plan would be that you first prove an inheritance lemma, and then you can prove a counting lemma with. And the inheritance lemma can be useful for other things as well. So with pseudorandom, now I mean this condition. So there is this condition of bijumbledness. So you have two. Basically, I'm just talking about. I'm just going to want to talk about pairs. So I'm going to talk about what happens between V and W. So we'll say it's P gamma bijumbled if every subpair, well, the edges between a subpair obey this bound. So, and this is the explanation for this is that if this was randomly like a pair, like a random bipartite graph, then this would be the expectation that you would have for the edges, and the variance would be something of this kind. So you're sort of measuring how far in the variance, how many times the variance you're away from the expectation. So it's not like it doesn't come from nowhere. So it doesn't. So it goes back to the 80s. Although maybe under this name of jumbled and not bijumbled, where they look at all the pairs, not only disjoint pairs, but it's not much of a difference. So in the end, it's all very similar. So, and for instance, you have that the random graph is jumbled. So the random graph, with edge probability P, is this jumbled, and this is essentially best possible. Because you can't be like really, you're better jumbled if this number is smaller, right? So that's basically, you cannot be much better than the random graph, which should make sense. And then there are several examples, like these ND lambda graphs. And you can have explicit constructions for bijumbled graphs. So now the plan would be you have a pseudo-random graph gamma and a subgraph G, and then you prove an inheritance lemma for that the regularity in the graph G is going to be inherited in a subpair, and then you can use this to show counting lemma in G. So, and the inheritance is to overcome this problem that we have. So the lemma that we have, and I'm going to compare this then with Condon, Fox, Zhao lemma, who had first such a lemma, a very similar lemma. So what we have is this. So we are starting in this situation where we are looking at a triple, and we have bijumbledness between these two, x and y, and we have bijumbledness between y and z. And that is in the underlying bijumbled graph gamma. And then in G, we have regularity here. So now, I'm sorry, this is slightly different than from my definition before. So this tells you something about the density. That is the density. So this is what we have, and never mind now what exactly is it saying here. It just says these two are like bijumbled. And in G, this is epsilon regular. And then you know that in this picture, so the neighborhood of a vertex, together with the whole other set Z, is going to inherit the regularity of this pair. So you have another epsilon, this is epsilon prime, but it's just like before. I mean, this would depend somehow on the epsilon side. So, and it's the other way around. And then we have this two-sided lemma where in the end, you will have, you look on both sides into the neighborhood of this vertex x. And then you need just one more jumbledness condition here. So that's what our lemmas say. And if I compare with the lemma of these people, they have, basically we only, so they have this number here, and they have p to the 5 half. So it's a bit better, but in the other lemma, we have this number, and they have 4. You can argue it's more beautiful, but ours is smaller. So that's the difference of the two. And what can you do with it? So you can do the counting lemmas, which is sort of, now I base the talk on mainly motivation, is the counting lemmas. So we have counting lemmas, which column functions are also had, but ours are like a little different. And yes, and sometimes they're better, so I said this depends on the graph. So we have this, so now we have two counting lemmas, and they're called one-sided and two-sided, but it's different one-sided and two-sided. Before this one-sided and two-sided was for the inheritance, was to say if I look at the neighborhood just on one side, and the other side is the whole set, or if I look on the neighborhood on both sides. But now this counting lemma just tells me this bound here, I'm talking about the numbers of copies of some graph H, is at least something. So that's just something different. So we have this. This is just what we wanted. I mean, it's just one side, but the rest of this is just what I had before in this counting lemma that we would like. And the conditions are that you have the regularity and you have the underlying bijumbledness in this partition, regular partition. So yeah, so no, yeah, it's not clear what this is. That's some parameter of the graph H that has to do with when you're in the enumeration of the vertices of H, you look at how many edges they send backwards somehow. So it's, yeah, I think I can't explain it. No. So in this lemma seems to be always at least as good as the lemma they have, and for some graph it's better. And then we have a two-sided counting lemma, and now we have, so now we can estimate it from both sides, so it's just plus minus gamma, and we have the bijumbledness condition now is this one here. So there is not only this parameter k reg, there's also this d tilde, which is something between the maximum degree of H and the maximum degree plus degeneracy. Or so yeah, there is a definition for this d tilde, which I also would like not to tell you, and but it's something between these two. So Yeah, so that's it, and that's for some graphs better. So what else can you do with it? So you can, we have this, then these people have shown a Blowup Lemma for sparse graphs. So the Blowup Lemma, I had this picture in the beginning, and so you remember more or less what that was. So, and they use this, they use the inheritance lemma for this here. So it's not only useful for the counting lemmas, and they also use this Blowup lemma for proving a bandwidth theorem for sparse graph recently. So that there are more applications that you could have for the inheritance. So just quickly, a bit of an idea how this proof worked for the one-sided inheritance, which was, well, in this picture here we have this bijumbledness, this regularity, and then you inherit this regularity in this pair. So you would first classify the pairs. So you take pairs of two vertices in Y. So here, and you look at what their neighborhood, so it will be here, what their neighborhood in Z, their joint neighborhood in Z looks like. So that can be, like, if I'm looking at it in G. So I will just say it's typical if it's as expected, more or less as expected or less in G, or it could be larger, or it could be really large. Then it would be, even if I look at it in this underlying bijumbled graph, then it is large. So that would be really exceptional. So those really won't happen so much, so I can just ignore them. And then I will classify vertices from here as bad if this pair, so that's now in gamma, so I should have drawn it maybe in yellow, but if this pair, I mean, no, this should be blue, but if this pair is too dense or if it's irregular. So, and then you can count and can say that then in this pair you have many more copies of C4 than expected. And then you can say the average pair has more common neighbors than you would have expected, and that's both in G, so that's all of this in G. And then you can say, yeah, then you must have many bad pairs in this neighborhood. So you could say if a vertex is bad, then you have many bad pairs in this neighborhood, in Y. But on the other hand, from the regularity of Y and Z, you know that there are not so many copies of C4. So again, through the C4 count, you know that there are few bad pairs overall in Y. So then there must be few triples X, Y, Y prime, so that Y, Y prime are bad. And then there are few bad X. And then you know, well, if you have few where this pair is too dense, then you also have few where it's too sparse. So then you just show there are few where this pair is too dense or irregular. So now you know there's few where they are not behaving well. So you must have that most are regular and of correct density. So that's like very rough overview. Yes, so and the proof of the two-sided is similar, but of course you have to do something different with the other neighborhood. Yeah, okay.
Okay, are there any questions from the speaker with Matthias?
So in one of these results we had some log factor in it, right? So that's maybe in the pseudorandom setting a little bit surprising. So that, I mean, in the random setting it's natural that you would sometimes have some log factors, but in the pseudorandom setting I haven't seen that so often. So is there any indication or how it comes up in the proof?
Yes, I think the log shouldn't be there. It comes out of the proof.
But it shouldn't be there, or should
No, I
it be?
think it shouldn't.
No, you estimate some sizes and you
Yeah.
need to partition where this
Ah.
neighborhood and you sum it up and log counts. That's
Yeah.
all.
Any further questions? Jacob?
So one of the things that we couldn't figure out, I guess it's very hard in the other direction to see what's tight and what's not tight. One of the problems is we don't have good constructions of pseudorandom graphs that are H-free, or maybe have smaller count. And I was just wondering if there was anything interesting to say about this, because this is kind of something that we were at a loss. There's like examples like Noga Alone's graph of a pseudorandom triangle free graph, and that's the wrong exponent compared to the upper bound here. And I think it was for the case of triangles. And for cliques, we didn't know what the right exponent should be. Was there any further insight about this?
I don't know.
No, but there seems to be some controversy about what should be the right thing for triangle, right?
Yeah,
Yeah.
yeah, so I think that's very interesting,
I
especially.
think you believe in Noga's construction.
I think this is
Yes.
it, yeah.
Sorry, you believe? I didn't hear that.
Yeah, we believe in Noga's construction.
But the bounds aren't tight,
Yeah.
and the pseudorandom in this work.
But I think you didn't believe that.
So we thought hard about this for a time,
Yeah, no,
and then,
yeah.
but we didn't, yeah. It's been a while.
Okay. Any more questions? Okay, if there are no more questions, let's thank the speaker again. And the